Okay, so now we want to find a potential for this vector field. In other words, we want to find a scalar valued function f such that the gradient of f is equal to this vector field. Well, first let's see if we can. So let's take the x derivative of this function, the y derivative of that function. If you take the y derivative of that function, you get 2y e to the x plus 1. And if you take the x derivative of this function, you get 2y e to the x plus 1. These two things are equal, so the previous theorem says that there is a potential. And not only that, the previous theorem tells us how to construct such a potential. And I'm going to go through a very detailed process here because there's some things I want to illustrate, but in the next problem we'll do kind of a more streamlined process. So f of xy, this is going to be the integral from t equals 0 to x of the function y squared e to the x plus y. And I'm not going to go on ahead and compute this function right now. And actually, this is e to the t, okay, plus phi of y. All right, I'm not going to exactly compute this function right now, but do note that if we take the derivative with respect to x, we get y squared e to the x plus y. All right, now if I take the derivative of this with respect to y, this is the integral t equals 0 to x, and I'm going to take the derivative of that with respect to y. The derivative of that with respect to y is 2y e to the t plus 1 dt plus phi prime of y. And now this, well, if I just compute this integral, this is going to be 2y e to the x plus x minus 2y, and then we're going to add phi prime of y. Okay, that is a partial derivative of f with respect to y, but we know we're picking f such that the gradient of f is equal to capital F. So we know that the partial derivative of this with respect to y is equal to 2y e to the x plus x plus 2y. Okay, so let me zoom out a little bit. Now, if I compare the left hand and the right hand side, look what happens. There's a 2y e to the x. That cancels with this 2y e to the x plus x. So the 2y e to the x plus x on the left cancels with the 2y e to the x on the right. Okay, and so what we're left with is phi prime of y is equal to 4y. Now, this is an important thing to mention here. If when we had done this cancellation, phi prime was not a function of y. In other words, if there was x stuff in there, it meant that we had done something wrong and we would need to go back and check our error. Okay, so phi prime of y is equal to 4y. So this means that phi of y is just going to be the antiderivative of the right-hand side. So this is going to be equal to 2y squared plus some constant. So in other words, f of xy is equal to this function here. And now I'll go on ahead and compute this antiderivative. So y squared e to the t plus y, when you do the antiderivative or the integral of that with respect to t, you get y squared e to the x plus yx minus y squared. And now we add in phi of y, which is 2y squared, plus some constant. Now, we just want any function f that satisfies the gradient of f is equal to big F. So it's easiest just to take the constant equal to 0. And now so I know this is getting kind of messy. Let me highlight what f is. So this is what f is here. Okay, and if you take the derivative of that function with respect to y, what you get is with respect to x, what you get is y squared e to the x plus y, which is exactly what that is. And if you take the derivative with respect to x, what you get, if you take the derivative with respect to y, you get 2y e to the x plus x minus 2y plus 4y, which ends up being plus 2y. Anyways, just take the derivative with respect to y of this highlighted portion, and you'll see that you actually get this portion right here. Okay, so this is, again, was kind of a tedious way to do this problem. We'll kind of see a more streamlined and perhaps more natural way of doing this in the next problem. But I just wanted to illustrate very explicitly how things match up with the proof that we just saw.